Now that we have a little bit of an understanding of continuity and discontinuity, here are some theorems, properties, etc., that really relate to continuity. So just as we have limits being from the left and right, we can talk about left and right continuity too. And it actually makes sense because continuity, right, is defined by a limit. So continuity from left and right makes sense. And so if it's continuous from the left, that just means that the left-hand limit, right, the left-hand limit is equal to the function value at a, and then similar from for the right, okay? And then, not surprisingly, if a function is continuous from the left and right at a, then it's continuous at a. That's kind of like, well, duh, right, limits and all that stuff. But nevertheless, it can be said. And then we talk about, so continuity up until now has been defined at a point, but then when we talk about a function being continuous, and then generally when we use just it's continuous, we mean on an interval, on its domain, on some larger set of numbers rather than just a point. That means it's continuous at every point in the interval. Okay. And then if we talk about endpoints, right, it would be continuous from the right at the left endpoint, continuous from the left at the right endpoint, which might take you a moment to process, but a picture might help. Okay. Um, and then unsurprisingly, because again, continuity is related, has its definition rooted in limits, right? If we have two continuous functions, and we have a real number constant, right? If we add or subtract continuous functions, it's continuous. If we multiply continuous functions, it's continuous. If we divide continuous functions, it's continuous, except for where the denominator would be 0, what the values that would make the denominator 0. And then also if we do a scalar multiple of a function, that would also be continuous, okay? So as a consequence of that, okay, again, we're going through a lot of propositions and theorems in rapid style motion. So there's a theorem that says if f is a polynomial, then it's continuous. If it's a rational function, then it's continuous on its domain, right? And so again, just for clarification, a rational function is continuous on R except for the values that make the domain or the denominator of that function equals 0. Okay. And when we say everywhere, that's all real numbers. And then third, it says the following functions are continuous on their domains: radical, trigonometric, logarithmic, and exponential. Oh, okay. So that's a very strong statement, but it kind of is a consequence of if we think about their graphs, right? What does a radical function look like? Trigonometric function, logarithmic, etc. They're all smooth curves that we can draw with a single swipe of our pencil. Okay, so we can maybe just outline some proofs here. So, for example, if we wanted to prove A, right, I would just say let f be a polynomial. And I'm going to abbreviate polynomial function fcn, so a little bit of abbreviation. So what f would look like would be something like a sub n x to the n plus a sub n minus 1 x to the power of n minus 1. That should be minus 1. And then plus dot 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 plus a1x plus a0. Okay. Then I would say for all x, or for all a, I in R. Nope, I want a in R, my bad. A in R, we would have, if we look at the limit as x approaches a, of f of x equals f of a. Okay, by linear operator properties, which we learned already. Props of limits. Okay, so this proof isn't terrible, it's just you need to know your definitions, right? So if we look at the limit of continuous, why are we able to conclude this? Well, it's because we know how limits work. We know the definitions and theorems of limits. Okay, and B, it's similar to a, I'm just going to write this as an outline. You would need to, so you need to use part A's proof in the numerator and denominator. Okay, because a rational function is defined as a quotient of polynomial functions, that's why A works. Okay, all right, some quick examples here that come as a consequence of this. So limit as x approaches 4 of all that stuff, and then limit as x approaches 3 of all that stuff. I want you to pause the video, try it on your own, and resume the video when you are ready to see the solution. Okay, so for this first one, if I look at this, so I know if I look at this function, this factors in the denominator is 2 parentheses 2x minus 1. And here, this just means that x cannot be 1/2, right? So what we just saw in part B is if we have a rational function, it's continuous on its domain. And 4, right? 4 is in the domain. So that just means if I call this whole thing f of x by continuity, this should just be f of 4. Okay, so then let's just evaluate 4. So I do 3 and then 4 squared minus 2 times 4, and then plus 1 over 4 times 4 minus 2. And if I do the arithmetic here, what I end up getting is 41 over 14. Easy, okay? Similar thing here, I just need to check that 3 is in the domain, and so natural log is the kind of picky one. So I'm just going to look at natural log, right? Natural log, I just need to know that for a log, right, I need the input to be greater than 0, and so this just means that x has to be greater than 2. 3 is greater than 2, so I should just be able to substitute in directly and say that this is natural log of 3 minus 2 over cosine of 3 pi. And the other thing I needed to is see where cosine is 0, and cosine of 3 pi, that gives me -1. Okay, so I didn't check that piece. I should have checked that piece, but yeah, sorry about that. Yeah, if it was cosine of a multiple of like an integer, so if it was like pi over 2, 3 pi over 2, 5 pi over 2, etc., then we'd be in an issue. But here we're okay, and then we just get 0, so this ends up being 0 for us. Okay, and that so that's a nice shortcut for us with evaluation. Last theorem. So we talked about adding, subtracting, multiplying, dividing, scalar multiple. Continuity of continuous functions is continuous. That's the punchline here. So this one takes a little bit of time to prove, but is not terribly difficult. Okay, so again, I want to think about, so f is continuous at b and g is continuous at a, and the limit of g of x as x approaches a is b. Okay, and so let's just start there. So what I know, if I want to prove this, I know that limit as x approaches a of g of x is b. Okay, but this is by definition g of a, right? Okay, so now what I'm going to do is since I have equality, I'm just going to maybe put this as a parenthetical remark. Since I have equality, what I can do is I can apply a function on both sides. Limit as x approaches a of g of x is equal to f of b. Okay, and then why can I do this? We know that this is okay since f is continuous at b. Okay, and then so this allows me to say that the limit is kind of interesting. It can actually come outside, and so I do limit as x approaches a of the entirety of f of g of x is equal to f of b, and then this gives me that this is the composition. So the composition is equal to, again, this would be in parentheses f of g of a. And so then that means that f of g is continuous at a. Okay, and so that gives me my desired property. All right, so again, lots of important concepts connected to continuous and discontinuous, and so make sure to really understand what these properties are doing, and also take a look at the proofs. They're kind of interesting and might be useful to you later on.